Welcome. Tonight, our journey takes us into a world that vanished so recently, in geological terms, that the bones are still fresh. We're going to La Brea, where slow black pools of asphalt preserved an entire predator community in near-perfect detail, and where radiocarbon dating gave scientists something rare, a clock precise enough to watch an ecosystem collapse in real time. What they found wasn't a slow, quiet fade across millennia. It was a convergence, fires, a shifting climate, and the arrival of a new kind of predator, all pressing down on the same animals at the same moment. Picture the La Brea Tar Pits on a warm afternoon. Not the museum version, not the reconstructed sculptures on the lawn, but the actual pools themselves. Small, dark, quietly bubbling patches of black asphalt seeping up through the ground in what is now the middle of Los Angeles, surrounded by traffic noise and city smell, and the completely ordinary texture of modern life. There's nothing dramatic about them. They don't roar or hiss. They just sit there, slow and patient and sticky, the way they've been sitting for roughly 50,000 years. The mechanism that made them so lethal is almost embarrassingly simple. A thin film of water collects on top of the asphalt because asphalt is denser than water, and water sits on the surface. An animal comes to drink, it steps in, and the tar grips its legs with a slow, irresistible force that it can't pull free from. Not in an hour, not in a day. The animal doesn't sink dramatically. It just stops being able to leave, and eventually, it doesn't. What makes La Brea different from almost every other fossil site on Earth isn't just the sheer number of bones they've pulled from those pools, though that number is genuinely staggering. It's what the asphalt does to the bones once it has them. Asphalt preserves collagen, the protein matrix inside bone, in a way that most burial conditions don't. And collagen is what radiocarbon dating actually needs. So, at La Brea, scientists aren't dating the surrounding sediment and estimating when the animal might have died. They're dating the bone itself. Direct, specific, tied to the actual animal. That's a level of precision that most fossil records simply can't offer. If you find this slow, quiet exploration of deep time something you genuinely enjoy, I'd be grateful if you'd subscribe and leave a like. It helps more than you might think. Most fossil records give us something blurry, a smear of time across tens of thousands of years, where we can say, this animal lived somewhere in this general era. La Brea gives us something closer to a photograph. A single predator community preserved in enough detail that researchers can ask not just what lived here, but when exactly it stopped living here. That's a different question entirely, and it turns out to be the question that matters most. The animals that ended up in the tar weren't random either. A trapped herbivore calls out, and predators come. A trapped predator struggles in the asphalt, and scavengers arrive. Each new animal drawn in by the last creates a self-reinforcing trap, layer by layer, season by season, century by century. What the pits preserved, without anyone designing it that way, was the food web itself. The connections between animals, the hierarchy of who ate whom, recorded in black. 7 megafauna species came out of those pools in large enough numbers to date. Mammoths, mastodons, saber-toothed cats, American lions, dire wolves, giant ground sloths, and short-faced bears. Researchers radiocarbon-dated 169 individual fossil specimens spread across all 7 of those groups. Think of each of those 169 dates as a single data point on a timeline, a precise moment when a specific animal died in a specific pool of tar, in what was then a warm, oak-studded grassland at the edge of a continent still slowly emerging from the last ice age. When those 169 dates got plotted together, the researchers expected to see a gradual thinning, fewer and fewer specimens across the centuries as populations shrank, a slow fade spread across thousands of years. That's what a climate-driven decline looks like in the fossil record. Species dropping out one by one at different times, following different pressures. That's not what they found. Every single one of those 7 species vanishes from the Brea record at the same moment, 12,900 years ago. Not gradually, not species by species over centuries. All of them together within the resolution of the dating method. One layer of sediment holds a complete, functioning predator community. The next layer holds nothing. The ecosystem doesn't thin out, it switches off. That date, 12,900 years ago, sits at the precise onset of a climate event called the Younger Dryas. And to understand why those two things line up so exactly, we need to go back and spend some time in the world those animals were actually living in before it disappeared. Before we get to the collapse, we need to spend some time in the world that was lost. Because without a real sense of what existed, the disappearance is just a number on a timeline, and it deserves more than that. Roughly 15,000 to 20,000 years ago, North America looked nothing like the continent we know. The Great Plains weren't the open, empty grasslands we picture today. They were part of something scientists call the Mammoth steppe, a vast, cold, dry grassland stretching from what's now Alaska all the way down through the American interior, dense enough and productive enough to feed animals of a size we genuinely don't have good modern comparisons for. If you could have stood somewhere in what is now Kansas and looked out across that landscape, you wouldn't have recognized it. Not the plants, not the sounds, and certainly not the animals moving through it. The Columbian mammoth stood 4 meters at the shoulder and weighed up to 10 tons. Let me put that in terms you can actually feel. 4 meters is roughly the height of a 2-story building, and 10 tons is heavier than most city buses. These weren't just large animals passing through a landscape. They were architects of it, knocking down trees, compressing soil with every step, tearing open clearings where grasses could grow, and carrying seeds across hundreds of miles in their dung. A single mammoth moving through a forest edge was doing the work of a slow, patient land manager, and the ecosystem around it had been shaped by that work across hundreds of thousands of years. Giant ground sloths operated on a different scale, but with a similar effect. Some species reached the size of a modern elephant, stretching nearly 20 feet from nose to tail. And they moved through forest edges, pulling down branches that nothing else could reach, stripping bark, eating in ways that no other animal in the community ate. Their foot-long claws weren't weapons, they were tools, purpose-built for grabbing and pulling vegetation at heights that smaller animals couldn't touch. And the seeds in their dung-fed plant communities that had, over eons, become almost entirely dependent on the sloths to spread them. When the sloths went, those plants went with them, or very nearly so. The predator community was equally without modern parallel. Saber-toothed cats carried canine teeth the length of a human hand, curved and serrated, built specifically for killing very large, thick-skinned animals. American lions were larger than any lion alive today, and short-faced bears could run down prey across open ground at speeds no modern bear comes close to. This wasn't a simple food web with a few species loosely connected. It was a deeply, tightly wired system where every animal's body plan, every hunting strategy, every seasonal movement had been calibrated against every other over an almost unimaginable stretch of time. Dire wolves ran in packs across the whole continent, and the density of their bones at Brea alone tells you they weren't rare. Over 4,000 individual direwolf specimens have come out of a single tar pit site. They were everywhere. They were common. The same way pigeons are common in a modern city, dire wolves were a routine, everyday presence across Ice Age North America. Let me know in the comments where you're listening from tonight and what time it is for you. It's always a quiet comfort to know. What all of this adds up to is a world that wasn't fragile. It wasn't barely holding together. It had survived multiple glacial cycles, survived the full cold of the last glacial maximum, when ice sheets buried much of the northern continent, survived warming periods before. These animals weren't living on some ecological knife edge. They were, by every measure we have, deeply resilient, ancient-born survivors of conditions far harsher than anything the late Pleistocene was throwing at them. And yet, within a few thousand years of 12,900 years ago, almost all of them were gone from North America. Not reduced, not pushed into refugia. Gone. Something about this specific moment in time was different from every previous cycle those animals had already come through. To start understanding what that something was, we need to look at what a sediment core pulled from the bottom of a quiet lake in Southern California actually recorded. There's a lake in Southern California called Lake Elsinore, sitting about 80 miles southeast of Los Angeles, and for thousands of years it's been doing something quietly extraordinary. Collecting the past, one thin layer at a time. Every year, dust settles, pollen drifts down, ash from distant fires floats across the water and sinks. Each year compresses into its own thin band of sediment at the bottom of the lake, so thin you'd barely see it, but distinct enough that scientists can count them the way you'd count tree rings. Stack 13,000 of those layers, and you've got a record going back to the edge of the Ice Age. Readable and precise, telling you not just what the weather was doing, but what was growing in the hills nearby, and what was burning. Scientists drill down into that sediment and pull out a core, a long cylinder of compressed time, and then work backward through it, century by century. Pollen grains tell you which plants dominated the surrounding hills in any given era, because different plants produce distinctly different pollen shapes, small enough to float on wind and sink into a lake, but durable enough to survive for tens of thousands of years in cold, dark sediment. Charcoal particles tell you when fire swept through the region, and roughly how intense those fires were, because more charcoal means more burning. What the Lake Elsinore core recorded, starting around 13,500 years ago, is one of the most striking signals in the entire sediment column. Charcoal levels don't creep upward, they spike. A sharp, sudden surge, unprecedented in the 50,000 years of sediment below it, peaking somewhere between 13,200 and 12,900 years ago. The hills around that lake were burning at an intensity the region hadn't seen in any era the core could reach back to. Not a bad fire season, not a dry decade, something categorically different from anything in the record beneath it. At the same time, the pollen shifts. Oak woodland pollen drops sharply out of the record, and fire-adapted shrubland species move in to replace it. The landscape that had fed large browsing and grazing animals for millennia was converting, not over thousands of years, but within centuries, into a different kind of place. Scrubby, low, fire-prone, sparse in the specific plant communities those animals depended on. And that dependency is worth sitting with for a moment. A large herbivore like a mammoth or a ground sloth isn't simply eating whatever's available, the way a rat or a crow might. Its body is calibrated to specific plants, specific caloric densities, specific seasonal patterns of forage. An adult mammoth needed something in the range of 300 pounds of plant matter every single day, and not just any plant matter. Woody browse, the kind of dense, calorie-heavy vegetation that oak woodlands produce, was central to that diet. When you burn through an oak woodland and replace it with scrubby, fire-adapted shrubs that grow back slowly and offer a fraction of the nutrition, you don't just change the scenery. You pull the food base out from under the animals that needed it most. The question the charcoal record raises, and that researchers have been working through carefully, is where those fires actually came from. A warming climate does increase fire risk. That's well established, but the pattern in the Lake Elsinore core is more intense and more sudden than climate warming alone typically produces. The warming that preceded the Younger Dryas was real, but it had been progressing gradually, and the charcoal record doesn't behave gradually at all. The timing of that charcoal spike overlaps almost exactly with the spread of human populations through Southern California. Early humans across many parts of the world used fire deliberately to drive game toward hunters waiting downwind, to clear terrain, to encourage the fresh green growth that attracts prey animals. That's a well-documented pattern in the archaeological record across multiple continents. The charcoal in the Lake Elsinore core doesn't tell us who lit those fires. It can't. But it does tell us that massive, landscape-altering fires were burning through the oak woodlands of Southern California at exactly the moment the megafauna vanished from the Brea record, and that those fires permanently rewrote the vegetation community. Climate and hunting were already pressing down on these animals. Fire was a third weight on the same stack, and the stack was getting heavy. Imagine the planet slowly warming after 20,000 years of glacial cold. Ice sheets pulling back from the coasts, sea levels climbing, grasslands greening across what had been frozen tundra for millennia. The world was, by any measure, recovering. And then, in a geological blink of an eye, the warming stopped and the cold came back. That's exactly what happened 12,900 years ago. The Younger Dryas wasn't a gradual cooling, a slow seasonal creep toward cold. It was an abrupt reversal, triggered by a massive pulse of cold fresh water pouring off melting glaciers into the North Atlantic and disrupting the ocean circulation system that moves heat around the planet. Think of that circulation system as a conveyor belt, carrying warm tropical water northward and releasing its heat into the atmosphere over Europe and North America. When that pulse of cold, dense fresh water flooded in, it stalled the belt. And without it, temperatures in parts of the northern hemisphere dropped by as much as 10 degrees Celsius within decades, possibly within years, not centuries, decades. For roughly 200 years, the warming stopped entirely. Glaciers re-advanced in some areas. The grassland steppes that had been slowly transitioning contracted back toward their glacial footprint. And then, around 11,700 years ago, the Younger Dryas ended just as abruptly as it had begun, and the warming resumed as if nothing had interrupted it. Now, the megafauna of North America had survived cold before. They'd come through the full glacial maximum, when ice sheets buried much of the northern continent under a kilometer of ice, and they'd done it across multiple cycles over hundreds of thousands of years. Cold alone wasn't what killed them, and we know that because they'd already proven they could handle cold. So why did this particular cold snap, shorter and in some ways less severe than earlier glaciations, line up so precisely with the collapse we see in the Brea record? The research points towards something specific about what the Younger Dryas did to a system that was already buckled. Before 12,900 years ago, the earlier warming had been fragmenting the mammoth steppe for centuries, breaking it into isolated patches separated by expanding forests and shifting vegetation zones. The mammoths and other mega-herbivores weren't living across one continuous habitat anymore. They were living in islands of it, getting smaller and more disconnected as the warming progressed. When the Younger Dryas arrived and froze that process in place, those fragments couldn't reconnect. They couldn't recover. The cold locked the fragmentation where it stood, and large animals with long generation times can't outrun that kind of change. A mammoth doesn't reproduce until her late teens, and her gestation period runs nearly 2 years. So a mammoth population that loses 30% of its range in a century doesn't have the reproductive speed to compensate. It just gets smaller, generation by generation, quietly and without drama, until the numbers drop into a range where the ordinary accidents of life become lethal. Biologists call this a demographic bottleneck. A small population is vulnerable in ways a large one simply isn't. More exposed to disease, to a drought that hits at the wrong moment, to the kind of random bad luck that a healthy population of thousands absorbs without noticing, but a stressed population of hundreds can't. Once you're below a certain threshold, recovery gets genuinely hard, even when conditions improve, because the genetic diversity needed for adaptation starts to erode, and the population's ability to bounce back from any single bad event shrinks with every generation. It's worth pausing on something the research makes clear. Previous rapid climate shifts of similar speed and severity, events called Dansgaard-Oeschger cycles, swept through the northern hemisphere during earlier parts of the Ice Age, without triggering mass extinctions of megafauna. The animals survived those. The Younger Dryas wasn't categorically more lethal than what came before it. What was different this time was everything else pressing down at the same moment: the burning hills, the fragmenting habitat, and a pressure that hadn't existed during any of those earlier climate swings. The Younger Dryas, then, wasn't the executioner. It was the final weight on a stack that had been building for centuries, the thing that pushed populations already stretched past the edge of recovery over a threshold they couldn't climb back from. What the Brea date of 12,900 years ago captures isn't a killing blow. It's the moment the cumulative weight finally exceeded what the ecosystem could carry. That something else arrived on 2 legs, and it had never been seen in North America before. Somewhere between 16,000 and 13,000 years ago, depending on which archaeological site you trust and which dating method you use, human beings entered North America for the first time. Not in any cultural sense we'd recognize today. No cities, no agriculture, no written language, but fully modern in every biological way that mattered. Cognitively complex, socially organized, capable of coordinated hunting across large groups, and carrying a technology that the animals of North America had never once encountered. The Clovis point, a finely worked stone blade hafted to a spear shaft, could kill an animal as large as a mammoth from a distance that kept the hunter completely safe. That distance changed everything. The debate about how much direct hunting actually drove the extinctions is one of the oldest arguments in paleontology, and it hasn't been settled. The overkill hypothesis, developed by ecologist Paul Martin in the 1960s and 1970s, argued that human hunters spread across the continent like a slow wave, killing prey that had no evolved fear of people, collapsing megafauna populations in as little as a few hundred years. It's a clean picture. It's also not quite what the evidence shows. Kill sites, places where human tools turn up alongside megafauna bones in a way that clearly indicates hunting, are surprisingly rare. We have solid evidence for humans hunting mammoths at a handful of locations and mastodons at a few more. But for most of the large animals that disappeared, the direct archaeological record of predation is thin, not absent, thin. That thinness doesn't mean hunting wasn't happening. It means hunting either occurred in conditions that didn't preserve well, or it operated at a scale that wasn't the primary driver on its own. What some researchers now favor is something called imperceptible overkill, and the name describes it exactly. Not a slaughter, not a blitzkrieg, just a hunting pressure slightly, consistently higher than what the populations could replace through reproduction, spread across centuries, nearly invisible in the ground, but cumulatively lethal across generations. Let me put it this way. Imagine a mammoth population of a few thousand animals, already contracting because of habitat loss and a fragmenting food base. That population doesn't need to be hunted hard to be pushed toward extinction. It just needs to be hunted slightly faster than it can replace its losses. Take 1 or 2 extra animals per year, per hunting group, across a continent filling slowly with hunters, and the math turns lethal over centuries without ever producing a single dramatic kill site that archaeologists would stumble across 10,000 years later. A 2023 study in Nature Communications looked at 139 megafauna species and found that 91% of them were already in population decline across the 50,000 years before their final extinction, and that the pattern of decline tracked human expansion across continents more closely than it tracked climate shifts. The populations weren't collapsing suddenly. They were being quietly eroded, generation by generation, long before the terminal moment we see in the La Brea record. That's a slow, quiet pressure. It doesn't look like a massacre. It looks like a gradual thinning of the herd across time, until the population drops small enough that a bad winter, a drought, a fire season, or a cold snap, like the Younger Dryas, can do what it couldn't have done to a healthy population of tens of thousands. The killing blow only works because the patient erosion came first. So the arrival of humans in North America wasn't a single catastrophic event with a clear before and after. It was the introduction of a new, accumulating weight into a system already bent under climate stress and burning hills. And we know humans mattered, even without the kill sites to prove it directly, because of what happened on the one continent where humans had lived alongside megafauna for an incomparably longer time. Africa still has elephants. It still has lions, hippos, rhinos, and giraffes. The Americas had ecological equivalents of nearly all of them, and lost almost every single one. That difference isn't random, and it isn't explained by climate. Africa experienced warming during the terminal Pleistocene too. Its megafauna largely survived anyway, and the reason why tells us more about what actually drove the North American extinctions than any kill site ever could. The reason Africa still has elephants is simple, and it's worth sitting with. 2 million years. That's roughly how long the ancestors of Homo sapiens and the megafauna of Africa have been sharing the same continent, the same water sources, the same seasonal migrations. African elephants didn't encounter modern human hunters as something new and unreadable. They encountered the ancestors of modern hunters and the pre-human hominids before that, across a stretch of time long enough for genuine behavioral adaptation to take root. They learned, generation by generation, to read the specific threat that a coordinated group of upright primates represented. They developed tight, protective social structures around their calves. They learned which open terrain left them exposed and which landscapes offered cover. That learning isn't cultural, the way ours is. It's written into their behavior at a level deeper than memory. Ecologists call this co-evolutionary trophic equilibrium. The predator and the prey shaped each other across eons, each side adjusting to the other until the relationship reached a kind of working balance. The prey got better at surviving. The predator got better at hunting. Neither side drove the other to collapse, because neither side was a complete surprise to the other. In North America, that balance never had a chance to form. The mammoths and ground sloths and short-faced bears that Clovis hunters encountered had spent hundreds of thousands of years developing responses to the predators they knew. American lions, saber-toothed cats, dire wolves. Fast, powerful, built for killing. North American megafauna weren't naive about danger in any general sense. They were naive about this specific kind of danger, a small, slow, bipedal animal that could kill from 30 feet away, coordinate with a dozen others, and specifically target the largest, most reproductively slow animals in a herd. From a mammoth's perspective, a human with a spear probably didn't register as a lethal threat at all. Strange, maybe. Worth watching, not worth fleeing. That absence of fear, that gap in the behavioral repertoire, is what Paul Martin's overkill hypothesis was really pointing at, even if the actual mechanism played out more slowly than his original model described. Australia makes the same point, with even more force. Australian megafauna disappeared somewhere between 46,000 and 43,000 years ago, well before any climate shift severe enough to explain the losses. The timing tracks almost exactly with the arrival of humans on the continent, and the animals of Australia had evolved in complete isolation, not just from human hunters, but from any large, intelligent tool-using predator at all. They were, in the most literal sense, behaviorally unprepared for what arrived. The continent's megafauna didn't stand a chance, not because they were weak, but because nothing in their evolutionary history had ever given them a reason to run from something that looked like a person. There's a quiet sadness in that. The mammoths weren't doing anything wrong. They weren't failing to adapt to something they could have adapted to, given time. They were behaving exactly as hundreds of thousands of years of successful survival had shaped them to behave. The rules changed faster than evolution could track, and that's not a failure. It's just a brutal mismatch of timescales. The Africa comparison also forces us to think more carefully about what ecological resilience actually means. It's not just about population size, or physical toughness, or how many centuries an animal has been around. It's about whether an animal's behavior includes the right responses to the specific threats it faces right now. African elephants carry those responses. Colombian mammoths didn't, because they'd never needed them, and there's no evolutionary shortcut for that gap. Africa experienced real climate shifts during the terminal Pleistocene. Human populations there expanded too, and their technologies developed across the same general era. Its megafauna largely came through anyway. That's not a minor data point. It's the clearest signal the fossil record gives us that neither climate change alone, nor hunting pressure alone, was enough to collapse a megafauna community. What it took was a naive prey population encountering a novel predator at the same moment that climate stress was already shrinking and fragmenting the habitat those animals depended on. And nowhere does that convergence show up more clearly than back at La Brea, where the carnivore trap recorded not just the disappearance of the prey, but the cascading collapse of everything that had been built on top of them. The tar pits didn't just trap animals that wandered in on their own. They trapped the entire food chain, one layer at a time, and the ratio of what they caught tells us something about how the Ice Age ecosystem actually functioned, and how it came apart. At most fossil sites, herbivore bones outnumber predator bones by a wide margin, because that's how healthy ecosystems work. Prey animals are common, predators are rare. There are always more deer than wolves, more elephants than lions. That ratio is one of the most consistent patterns in ecology, and it holds across every continent and every era we have good fossil records for. At La Brea, the ratio is inverted. Predators and scavengers crowd the record in numbers that no natural population would produce on its own, with dire wolves and saber-toothed cats especially overrepresented, pulled from the asphalt in densities that only make sense when you understand the trap's mechanism. A mammoth gets stuck, it struggles, it calls out, and the smell of a large, distressed animal carries a long way across open grassland, so predators come, drawn by what looks like an easy meal. Those predators step into the tar. More arrive, more get stuck. The pits became a self-concentrating trap, pulling in carnivores in waves, each wave drawn by the last, so what got preserved wasn't a random cross-section of the animal community. It was a picture of predators clustering around a single stuck prey animal in numbers that, when you think about it carefully, suggests something was already going wrong. A healthy predator in a healthy ecosystem doesn't mob a trapped animal. It hunts. It ranges across territory where prey is available and relatively easy to find. The carnivore trap behavior, the clustering, the crowding around a single struggling herbivore, scales up when free-ranging prey is getting hard to come by. The overrepresentation of carnivores at Brea isn't just a quirk of the trap's geometry. It's a signal that the predator community was already under pressure, already concentrating around whatever food sources it could find, long before the final collapse at 12,900 years ago. When the mega-herbivores finally dropped out of the Brea record, the carnivore community didn't just lose a food source, it lost the ecological foundation its entire body plan had been built on. Saber-toothed cats carried those enormous curved canines because they evolved specifically for killing very large, thick-skinned prey. Animals with hides and muscle mass that required a different killing technique than anything a deer or a rabbit could provide. American lions were sized for taking down animals that no longer existed anywhere on the continent. Short-faced bears had a body optimized for running down prey across open steppe, and the steppe was being replaced by forest. These animals couldn't simply switch diets. A saber-toothed cat isn't built for catching rabbits the way a coyote is. Its whole body is built around one thing, and when that one thing disappears, the cat disappears with it. They followed the mega-herbivores not because they were hunted or outcompeted, but because the food web they depended on had been pulled out from under them, silently and completely. What survived was a simplified predator community, the generalists. Coyotes, small and flexible and willing to eat almost anything, came through. Pumas survived for the same reason, adaptable enough to shift prey when the ecosystem changed around them. The specialist predators, the ones whose bodies and behaviors were finally calibrated to the Ice Age prey community, were gone within centuries of their prey base collapsing. And it didn't stop with the predators. Scavengers that fed on mammoth carcasses lost their primary food source. Plants whose seeds moved through the gut of a ground sloth lost their dispersal mechanism. Smaller animals that sheltered in the open habitats mega-herbivores maintained through grazing and trampling found those habitats closing in as woody shrubs reclaimed ground that hooves and trunks had once kept open. The disappearance of 7 megafauna species from the Brea record at 12,900 years ago wasn't the end of 7 animals. It was the moment a food web that had been stable across hundreds of thousands of years dropped below the threshold it needed to sustain itself. And the ripples of that collapse are still visible in the simplified, quieter predator community of modern North America, where coyotes fill the space that once belonged to dire wolves. While the last mammoths on the North American mainland were dying, a small population had found refuge in a place so remote and so cold that the pressures reshaping the continent below simply couldn't reach them. At least not yet. Wrangel Island sits in the Arctic Ocean, north of Siberia, a place of flat tundra, freezing fog, and a solitude so complete it's hard to imagine anything surviving there at all. Around 10,000 years ago, rising sea levels cut the island off from the mainland, and a population of woolly mammoths was already living there when the water closed in around them. Rather than dying out with their mainland relatives, they kept going. For another 6,000 years, they grazed that frozen ground in isolation, and the last of them died roughly 4,000 years ago. To put that in terms you can actually feel, the Egyptian pyramids were already standing. Humans were smelting bronze, and somewhere on a cold Arctic island, the last mammoths on Earth were still alive. They weren't just a curiosity, those Wrangel mammoths. They were a window into something researchers still find genuinely complicated. What actually happens to a large animal population when it's cut off from the rest of its species and left to survive in a small, bounded world across hundreds of generations? Genomic analysis of Wrangel mammoth DNA revealed a population that went through a severe genetic bottleneck, a dramatic compression of genetic diversity caused by that small founding population being all they had to work with. Harmful mutations accumulated in the genome in ways that wouldn't have happened in a large connected mainland population, where those mutations get diluted across thousands of individuals. For a long time, the assumption was that this bottleneck amounted to a slow death sentence, a genetic unraveling playing out quietly across centuries until the population simply became unviable. But the actual genomic data didn't tell that clean a story. The Wrangel mammoths appear to have partially purged those harmful mutations through a process called purifying selection, where the most genetically damaged individuals failed to reproduce, gradually cleaning the genome of its worst accumulated problems. It's a slow, generational filter, not a cure, but it bought the population real time. They were small and isolated, yes, but the genetics alone didn't doom them. What the Wrangel record shows, when you step back from it, is that small populations can persist for a very long time if the environment around them stays stable and the pressures stay manageable. The island gave the mammoths something the mainland couldn't: no human hunters, a food supply that was bounded but sufficient, and freedom from the burning and habitat fragmentation that had torn apart the continent to the south. Wrangel was, in a very real sense, a refuge built by geography. The mammoths finally disappeared from Wrangel around 4,000 years ago, and the cause is still genuinely debated. Some researchers point to evidence of human arrival on the island around that same period. Others argue that a combination of shrinking genetic diversity, resource stress, and possibly disease pushed a population that was already small past whatever minimum threshold it needed to keep recovering from losses. It may have been, as with the mainland extinctions, several pressures arriving at once rather than any single killing blow. St. Paul Island in the Bering Sea tells a parallel story. Woolly mammoths survived there until roughly 5,600 years ago, and the evidence from that site points specifically to freshwater shortage as the final pressure, a resource scarcity that a small, island-bound population simply couldn't outlast or move away from. That's what isolation costs you in the end. A large, connected population can absorb a local drought, a disease outbreak, a bad breeding season, by drawing individuals from elsewhere and letting numbers recover. An island population can't do any of that. Every bad event hits the entire population at once, and there's nowhere else to draw from. The islands bought the mammoths thousands of years they wouldn't otherwise have had, and that's not nothing, but the walls of geography that protected them also made every stressor that did reach them more lethal than it would have been on the open continent. The last mammoth on Wrangel Island died in a place that humans had probably only just found, on an island that the rest of the world had forgotten existed. There's a concept in ecology called a ghost niche, and it's exactly what it sounds like. The empty shape a species leaves behind in a food web after it's gone. Not a metaphor. An actual, measurable gap in how energy moves through an ecosystem. Still present, still influencing everything around it, long after the animal that carved it out has vanished from the earth. North America is full of these gaps. The avocado is one of the clearest examples we have. Its seed is far too large to be dispersed by any animal currently living on this continent. And that's not an accident of evolution. It evolved specifically to pass through the gut of a giant ground sloth, whose digestive system was large enough to process it whole and deposit it, intact and fertilized, somewhere far from the parent tree. When the sloths disappeared 12,000 years ago, the avocado lost the only dispersal mechanism it had ever known. It survived because humans found it useful and spread it deliberately across the continent and eventually the world. Without that intervention, it almost certainly would have followed its disperser into extinction. The pronghorn antelope tells a different version of the same story. It's the fastest land animal in the Western Hemisphere, capable of sustaining nearly 90 kilometers per hour across open ground. And there's nothing alive on this continent that can come close to catching it. No wolf, no mountain lion, no coyote pushes it anywhere near that speed. The pronghorn evolved that speed to outrun the American cheetah, a predator that went extinct around 12,000 years ago. So the pronghorn runs, every single day, from an animal that no longer exists. It's still running from a ghost. These aren't just biological curiosities, interesting footnotes in a natural history textbook. They're evidence that the megafaunal extinctions didn't simply remove animals from the continent. They restructured the continent itself in ways that are still working themselves out. Nutrient cycles shifted when the massive dung producers disappeared, because the dung of a 10-ton mammoth moving across hundreds of miles of grassland was doing real, measurable work in how minerals moved through the soil. Vegetation patterns changed when the animals that maintained open habitats through grazing and trampling were gone, and woody shrubs moved into ground that hooves and trunks had once kept clear. Some researchers argue that parts of North America are still in ecological disequilibrium, still slowly adjusting to a loss that happened 12,000 years ago. The ecosystems we're trying to conserve right now, the ones we think of as natural and intact, may themselves be artifacts of that ancient disruption. And this is where the past stops being just the past. The same converging pressures that collapsed the La Brea ecosystem are operating right now on the large animals that remain. African elephants face shrinking habitats, a warming climate, and direct human pressure simultaneously, in exactly the combination that proved lethal in North America at 12,900 years ago. Rhinos and hippos face the same convergence. The pattern isn't new. We've seen where it leads. The de-extinction movement, the effort to resurrect woolly mammoths through CRISPR gene editing, has drawn a lot of attention, and the science genuinely is advancing. But most ecologists are cautious, and their caution makes sense when you think it through carefully. You can't reconstruct a genome. You can't reconstruct the mammoth steppe. You can't bring back the plant communities, the soil chemistry, the predator relationships, the seasonal migration corridors that the mammoth was woven into across hundreds of thousands of years. A mammoth without its ecosystem isn't a restoration. It's an animal out of context. The more tractable version of that idea is rewilding, returning wolves, bison, and large grazing animals to landscapes they haven't occupied for centuries, letting ecological functions slowly reassemble around them. It's already happening in parts of Europe and North America. and the results, while incomplete, are real. What the La Brea record teaches us, in the end, is the specific set of conditions under which a complex, ancient ecosystem can cross a threshold it can't come back from. A warming climate, a novel pressure that populations haven't had time to adapt to, and a physical transformation of the habitat those populations depend on, all pressing down at once. The bones in the tar are 12,900 years old. Tonight, as you settle into sleep, consider that the world outside your window is still carrying the shape of what it lost, still running from ghosts, still adjusting to a silence that fell at the end of the Ice Age and hasn't fully settled yet. We started tonight at a black pool in Los Angeles, watching 169 radiocarbon dates collapse onto a single moment, not spread across centuries, not thinning gradually, all at once. At 12,900 years ago, at the exact onset of a climate reversal that found a continent already burning, already fragmented, already quietly losing animals that had no learned fear of the thing hunting them. The answer isn't climate, or fire, or hunting, it's the overlap. Warming dried the land, fire rewrote the vegetation, and hunting pulled slightly faster than populations could replace their losses. And those three forces fed each other in a loop that populations below a certain size simply couldn't climb out of. Consider subscribing to continue these journeys through the lost worlds that shaped our own. The next time you see an elephant, or watch a wolf move through trees, or notice an avocado on a shelf, you're looking at a survivor of something enormous, and at the shape of everything that didn't make it through.